Hello everyone and welcome to the section 4 example problems for abstract modern algebra. So we have 8 example problems that we're going to work. So let's take a look at the first problem that we have here. So for the first problem we are asked to find the order of the given permutations and we need to state whether they are even or odd. We have alpha and beta, those two permutations. So let's see if we can work this problem. So let's take a look at alpha and see what's going on in alpha. So for alpha, we have 1 goes to 3, goes to 4, goes to 7, which goes back to 1. And then we also have 2 goes to 5, goes to 6, goes to 2. So if we were to write this in cycle notation, we would write it as this. So we are asked to find the order of this permutation. So the order of alpha is the order, we'll write it as order of pi, and we have a 4 cycle and a 3 cycle. So the least common multiple of 4 and 3 is 12. And there's our order for that permutation. Now let's see if we can figure out if this permutation is even or odd. So we need to write it as 2 cycles. Well, for our first permutation, we will have 1, 3, 1, 4, and 1, 7. Then for our second one, we will have 2, 5, and 2, 6. So this is 5, 2 cycles. So alpha is odd. All right, now let's take a look at beta and see what's going on in beta. Let's see here. For beta, we have 1 goes to 2, goes to 3, which goes to 5, which goes to 7, which goes back to 1. And then we have 4, goes to 6, goes to 8, goes to 4. So let's write beta in cycle notation. 4, 6, 8. And then let's find the order of beta. The order of pi, which is the least common multiple. We have a 5 cycle and 2 cycles, so 5 and 2. And that gives us 10. So there's our order for beta. And then let's split beta up into 2 cycles. Oops, it's supposed to be 1, 5. So we have 6, 2 cycles. So beta is even. And that's all we need to do for this first problem. All right, let's move on to problem 2. So problem 2, we are asked to write this permutation as a product of disjoint cycles. So this might seem kind of daunting at first, but this problem actually really is not as complex as it looks. So I think probably the easiest way to figure this out is to write this in disjoint cycles. So let's see if we can do that first. So remember, for disjoint cycles and for compositions of permutations, we go from right to left. So let's take a look at our first cycle here. I'll try to notate it up here. We have 1 goes to 2, Then we'll go to 2 over here. We find that 2 goes to 7. And then 7 goes to 8. So that's where this mapping comes from. 1 goes to 2, goes to 7, goes to 8. And then we'll do the same thing for the other elements. We'll find that 8 goes to 8. Since there is no 8 in the first 2 cycles, we just assume that it maps to itself, because if you remember, that was one thing we talked about in the lectures, which goes to 4. And then we have 4 goes to 5, goes to 2, goes to 2. Then we have 2 goes to 4, goes to 4, goes to 1. And take a look at some of the other elements here. We have just trying to find out where my pen was. There it is. Let me see if I can erase that little spot there. We have 5 goes to 6, goes to 6, which goes to 6. Then we have 6 goes to 1, goes to 1, goes to 7. Then we have 7 goes to 7, goes to 5, goes to 5. So let's see if we can form some disjoint cycles from these. So let's take a look at the first 4 that we have. We can combine them together. Oh, there we go. My pinkies go in different places. Here we go. So this can be a cycle of 1, 8, 4, 2. And then for the second one, this can be a cycle of 5, 6, 7. So we can rewrite this as 1, 8, 4, 2, and 5, 6, 7 raised to the 40th. Now we can simplify this even further, and we can do that by using modulos. We can do that by looking at the structure of the 2 permutations that we are working with. So we have 1, 8, 4, 2. Well, that has a, let's write it like this actually. This is a 4 cycle. So 1, 8, 4, 2 raised to the 40th is logically equivalent to 40 modulus 4, which equals 0. So 1, 8, 4, 2 raised to the 40th equals epsilon, and which is 1, or our identity permutation. And then we can look at 5, 6, 7. Well, this is a 3 cycle. So 5, 6, 7 raised to the 40th is logically equivalent to 40 modulus 3. Let's try to space this out where it's a little cleaner, which is equal to 1. So 5, 6, 7 raised to the 40th just equals itself, 5, 6, 7, since it's logically equivalent to 1. So therefore, this cycle raised to the 40th equals epsilon times 567, or 1 times 567, which is 567. And this is our answer. All right. That is it for problem 2. So let's take a look at problem 3. So for problem 3, we have the message, all these letters, T, M, E, M, E, T, H, A, E, T, R, K, P, A, has been encrypted using the permutation alpha, and we are asked to decrypt it. Okay, so how are we going to do this? Well, let's take a look at what we'll do. So, to decrypt the message, let's use alpha inverse. So in alpha, we have 1 going to 4. Instead, we will use alpha inverse 4 goes to 1. So let's start by breaking the message into 5 letter blocks. So our message is T, M, E, M, E, and then T, H, A, E, T, and then R, K, P, E, A. So let's take a look at our permutation. So we're doing the inverse of the permutation. So we will have 4 going to 1. We'll have 5 going to 3. And then we will have 3 going to 2. 2 going to 5. And 1 going to 4. So let's break this one up first, and I'll kind of walk through this and then just give kind of the answer for the rest of the other 5-letter blocks, showing how this works. So we have our 4th letter is going to go here at the start, at the first block. So we will have M. And then we have our 5th letter going to our 3rd block. So we have E. And we have our 3rd letter going to our 2nd block. So this was supposed to go here. I mean, that's the same letter, but still, I wanted to just make sure I was doing the steps right. Then we have 2 going to 5. So we have M. Then we have 1 going to 4. Looks like I did it wrong again. T is supposed to go here and M is supposed to go here. So yeah, that's kind of how this will work, and we'll do the same thing for the other 5 letters and blocks. So I will just go on and write down what those are. So let's put them all together and see what our message is. So we have So this is all one word, but you can figure out what it is and space the words out and see that the message is meet me at the park. And this is our message that's been decrypted. And this is an example of how encryption is done using permutations. because something similar is done on like a website, say when you put like your credit card number in to help prevent it from getting stolen. They might use encryption, which is very likely a permutation, to scramble it up where it can't easily get found out. Of course, we were able to decrypt this because we know the permutation, but that makes it real hard for someone that doesn't know what the pattern is to be able to descramble the message or decrypt the message. So that's just kind of a neat little real life example that permutations can be used for. All right, problem 4. We have H is the set alpha, which is an element of Sn, and we have the permutation of alpha of n equals n, where n is greater than or equal to 3. So we are asked to prove that H is a subgroup of n. Well, let's write out our proof strategy for how we're going to do this. So for a subgroup, remember we use subgroup test. So we will use the two-step subgroup test and show that alpha composed with beta is in H whenever alpha and beta are in H, and alpha inverse of n is in H whenever alpha is in H. Because if you remember from section 2 for the two-step subgroup test, the general form was saying that if we have A and B in H whenever A and B are in H, and A negative or A inverse in H whenever A is in H, then it's a subgroup of the group. And we're doing the same thing here, just using the properties that we have for permutations, because we're using composition instead of multiplication, and inverse permutation instead of an inverse element, because it's the same concept. So let's write out our proof. And where's my pen? It's up here with the letters. All right. So let's let H be the set that we were given. So since E is an element of Sn, where E is the identity, then we have the permutation of E of n gives us the identity. So thus the identity is an element of H, and H is non-empty. Because remember, that's another part of the subgroup test, is that our subgroup has to be non-empty. So we can just show it has an identity element to prove that. And then let's let alpha and beta be elements of H. So then we have alpha n equals n, and we also have beta n equals n. So the composition of alpha and beta, or the permutation of the composition alpha beta for n, is going to be alpha beta n, which is alpha n, which is n. So thus, composition of alpha and beta is an element of H. And then the last step we need to show is we're going to let alpha be an element of H. So then we have alpha inverse of alpha of n equals alpha inverse of n, which is n. So thus, alpha inverse is an element of H. So therefore, H is a subgroup of Sn as desired. And this proof is done. We did our two-step subgroup test and proved that H was a subgroup of Sn. All right. Let's take a look at problem 5. So we have beta as a 28 cycle, and we are asked to describe the cycle structure of beta squared, beta to the 4th, and beta to the 7th. Okay, so let's take a look at this. So for a permutation cycle beta, we have, or for a permutation cycle, let's call it beta n, where n is a natural number, represents the formation of 28 divided by n cycles. That make it up. Okay, let's write it like this, because we need to let our permutation cycle be beta. And then we're looking at beta raised to the n and seeing how many cycles make it up. So, since beta is a 28 cycle, we have the greatest common divisor of 28 and 2 is 14. So we have beta squared is 214 cycles. And then for beta raised to the 4th, we have the greatest common divisor of 28 and 4 is 7. So we have 7 cycles. And then for beta raised to the 7th, we have the greatest common divisor of 28 and 7, which is 4. So that gives us 4 cycles. And yeah, that's all there is to this problem. Here we go. Here's our itty bitty diamond. All right, yep. Let's take a look at problem 6. For problem 6, we are asked how many elements of order 3 are in A4, and then how many elements of order 5 are in A9. Okay, so let's take a look at this problem. So the order of A4, if you remember when we talked about in the lecture, it's n factorial over 2. So we have 4 factorial over 2, which is 24 over 2, which is 12 elements. So for an element to have an order of 3, the least common multiple of its disjoint cycles must be 3. So 3 cycles are the only elements with this order in A4. So we have 12 divided by 4, or 3, sorry, 3. We have 4 choices of 3 cycles. And we also have, since they can be 2 disjoint 3 cycles, we have 4 times 2 equals 8 elements. All right, then for the second one, we have for elements of order 5 and A9, a cycle structure where the least common multiple is 5 is where we have the least common multiple of 5, 1, 1, and 1, and 1, or a 5 cycle and 4, 1 cycles. So 9 factorial is very large. So we can instead find the elements using this formula 1 over 5 times 9 factorial over 9 minus 5 factorial, or 9 factorial over 4 factorial times 1 over 5, and that gives us 3024 elements. And yeah, that is it for this problem. Yeah, for this problem, there's not really a direct way you could solve these kind of ones, but you more just kind of have to look at what you have and try to logically reason through what you've got for these. All right, problem 7. We are asked to prove that the cycle 1, 2, 3, 4, 5, 6 is not a product of 7 cycles, and then we are asked to generalize it. Okay, well, this should be a pretty easy one to prove. So let's take a look at our proof. So let's But let's just state that 1, 2, 3, 4, 5, 6 is a 6 cycle. So then we have 1, 2, 3, 4, 5, 6. Let's break it up into 2 cycles. 1, 6. So 1, 2, 3, 4, 5, 6 has 5 2 cycles and is an odd permutation. So now let's define a general element, a general 7 cycles. So let's just define it as A1, A2, A3, A4, A5, A6, A7, be a 7 cycle permutation. So then we have A1, A2, A3, A4, A5, A6, A7. Let's break it up into 2 cycles. We will have, scroll down here, A2, A3, oh, that's not right, A1, A3, A4, A1, A5, A6, A1, A7. So A1, A2, A3, A4, A6, A7 has 6 2 cycles and is an even permutation. So since 1, 2, 3, 4, 5, 6 and a 7 cycle have different parities, they cannot have the same structure. So therefore 1, 2, 3, 2, 3, 4, 5, 6 is not a product of 7 cycles as desired. Now that we have completed our proof, let's generalize this statement. So here, start our generalization. One second, find where my pen is. So our generalization, let's let K be a natural number and K be a permutation. Let me write write this down here. So if k is odd, then no even cycle n, where n is a natural number, can be written as a product of k cycles. So basically what this generalization is, it's basically summing up what we showed in our proof, just in more general, abstract manner. All right, let's take a look at our last problem, problem 8. So we have alpha is a permutation, and we are asked to prove that alpha and alpha inverse will always have the same parity. Okay, this should be a pretty straightforward proof. So let's let alpha be a permutation. We proceed by cases on alpha. So we're going to do a case where alpha is even and alpha is odd because we're looking at parity. So only 2 cases for this proof. So for case 1, we have alpha is even. So then we have alpha is beta 1, beta 2, so on and so forth up to beta 2k, where beta is a 2 cycle and k is a natural number. So thus we have alpha inverse is going to be beta 2k, beta 2, beta 1. So therefore, alpha inverse is even. Now let's look at our second case. So we have alpha is odd. So then we have alpha equals beta 1, beta 2, beta 2k plus 1. Try to make that a little cleaner. Where beta is a 2 cycle and 2k plus 1, or yeah, let's do k is a natural number. So thus we have alpha inverse is beta 2k plus 1, beta 2, beta 1. This is cycle structures, so therefore alpha inverse is odd as desired. Yes, so that's basically how we were able to prove this is we can define alpha by the broad two cycle structure, because you remember back in our lectures when we looked at even and odd permutations, we defined a permutation with that abstract cycle, which was used using some of the Greek letters like alpha and beta. And by showing that they're even and odd, we can show that their inverses are even and odd because it's basically just the reverse of the cycles. So, all right, that is it for the section 4 examples. Thank you guys so much for watching, and there will be 2 bonus lectures for this section if you're interested in watching those. So thank you so much. Really means a lot that you are watching these, and I hope these videos are helpful and beneficial to you. Please leave a like and comment if you have any thoughts. Thank you.